Perfect. And we're going to start this webinar now. Welcome, everyone. Thanks for joining us today. We have a little bit of a specialized topic today where we're going to talk specifically about measurement and verification for industrial project and how to use option D of the IPMVP for these industrial projects. So without further ado, our speaker for today, Eric Mazzi, will take it away.
Hi there, welcome everybody. My name is Eric. Pleasure to see some familiar names attending the webinar, so welcome to everybody. So I'm Eric. I'll just, I guess, introduce myself briefly, and then we'll get on with the topic. So my background is mechanical engineering and policy. Probably about 10 years ago, I started getting seriously into M&V. I find it's really important, and I really enjoy doing measurements and measuring real world systems. So I really enjoy doing the M&V work for a variety of processes. I've been a member of the International Protocol Committee for about 8 years. A little earlier than that, about 10 years ago, I joined as a contracted member of BC Hydro's industrial M&V team, and I continue to today. A really excellent group and team there, and a lot of colleagues that I've learned from. I've also enjoy educational things, so I am a CMVP trainer, as noted there. And yeah, the topic for today is measurement and verification for industrial projects, specifically option D. And for those who may not know, option D is the terminology of the IPMVP is it has these methods A, B, C, D, and we're going to talk about what option D is. So I recognize that there are some people with a good industrial experience in attendance, so I'm hoping you folks will keep me honest and engage in some discussions here. So what we're going to do is just go over very briefly what is this so-called option D, what is the method, and then we're going to talk about 3 real-world case studies. These are real projects, realistic numbers, although I've altered numbers so as not to unintentionally share data that I'm not supposed to be honest. But the case studies are definitely based on real case studies. And we'll just go over really what is the option D and why I use it. And then the 3 case studies, one is based on an oil pipeline, one on a water treatment plant, and one on a natural gas processing plant. Just at the outset here, to get an idea of what you folks, where you're coming from, I have this survey to do to start. So if you go to use your computer or cell phone, likewise, great to see you, Ali, in the chat there. Yeah, so if you go to menti.com and enter that code, you see 3528-1411. Okay, so I just put that in the chat. So yeah, I would like to know what is your role in M&V, or maybe where do you aspire to go with M&V if you're really not working in M&V at this point? Yeah, I'd like to get an idea. So it looks like we got 50 people in the course, or 49. I hope we get 49 responses. That would be nice. Give it another 30 seconds-ish. We're up to 26 responses. Thanks for folks taking the effort. Okay. So quite a few people who are part of a team doing M&V. Several of you are the lead. Some of you are hiring M&V professionals or providing financial support, a lot of general interest. So very good. Excellent. Okay. that is helpful for me. Get back to actually, let me see if I can, in case you folks are interested, if I can do this, it should work. I'll put our survey results in the chat. Usually works in Teams. There we go. Should see it shortly. Okay. Okay, there are some abbreviations. These are shown here. Maybe I'll put these in the chat too. I'm kind of obsessed about abbreviations and minimizing my use of them, to be honest. So those are just for reference. Okay, so this is the fourth and final of a 4-part webinar series that I've done, and there are links here for the other 3. We did one on introduction to M&V, one on low-cost M&V options, one on high-value, really higher-cost M&V, where that is warranted and justified. And so this fourth and final seminar is the industrial option D that we chose as a topic. Okay, for any kind of M&V, this is my professional opinion and overlaps with a lot of other people's. It overlaps with, for example, the IPMVP. It's important when planning M&V. These are, first of all, it's critical to do an M&V plan, and it's critical to think about these steps that are outlined here. Looks like we got a little background noise, Melis. Maybe we could mute. But yeah, so I'm definitely of the opinion that it's very important just to think through this bullet list of items, even if you're doing some quick and dirty like an option C or whatever the project is. From one perspective, to me, there's no excuse for not just going through this checklist. Think about what are the reasons for investing in M&V. Take the time to describe your energy efficiency measure and the measurement boundary. You need to think about what are the key variables. It's very critical, in my opinion, to identify who is the lead M&V professional. I mean, that person could change over the course of a project, but at any point in time, there really needs to be a point person. What are the variables that are going to be metered? Do conduct site verification. All these steps, I've been involved with projects where some of these, or every one of these has been skipped in a real world project that I've been involved with. In some cases, people wanted to skip, or at least tried to skip, the site verification. I argue, well, that's critical, essential, and you're really running at some risk for not doing site verification. You want to think about your analysis, how you're going to do it, and what methodology. Think about the reporting, who's going to do it, how, when is the reporting, and so on. So these are just a quick and dirty list of, if you're involved in M&V, have an M&V plan. I can see that all of these bullet items could be done in a 2-page document if you needed to. Just keep it short, table format. Just identify these, go through this checklist, if you will. So what is the option D method? Where does option D come from? Well, option D, it's the method for when energy simulation software is used for M&V purposes. So that comes from the IPMVP core concepts. So when we talk about simulation software, we're talking about software that's based on engineering or physics equations, if you will. Statistical models typically are not what one would consider an option D method. And it's also important, this differs a little with what's in the IPMVP, and frankly, that I hope to see that little nuance corrected at the next update of the core concepts. But option D is not necessarily whole facility. It can definitely be system specific, which is exactly what we're showing in these case studies. We're using option D, and it's not the whole facility meter. For a building, it probably would be likely a whole building. For industrial applications, definitely not necessarily at all. So we're talking about models and data in IPM option using computer simulation models and the option D. So I'm going to do a very quick basic review of what's the difference between models and data. And we're really just talking basic science here. And we're always, so this is just from a philosophy of science textbook that I've used for myself and a lot of educational purposes for 15 years. So what we're doing when we're doing basic science, which is equivalent to saying, what are you doing when you're doing M&V and measurement and verification? Just a note in the chat, I guess one person says they can't see my screen, but I assume everybody else can. So not sure if there was, yeah. I'm assuming it's not everybody cannot see it, but if there's an issue, someone in Malis, I guess, interrupt me. Okay, so this is basic science, basic M&V. You start with what is the real world system, right? We already mentioned M&V, one of the basics. What's your measurement boundary? What's your system boundary? And then we're going to use models. Well, what are models? There's all different types of models. You can do physics equations, statistical equations such as regression. You can use visual models. You can use computerized spreadsheets just in the form of a bunch of numbers representing a real world system. You can do physical models. I've been in projects where, two different projects in my career where a physical scaled model was built. One was for a stormwater drain pipe. One was for a boiler. A scaled model of a boiler was built with plexiglass. I actually did another one myself. So physical models, meaning you physically build a benchtop model and you test something. Those are also very much valid modeling method. And so what are models doing? Well, we want to make predictions of energy consumption, but this is very broadly in science. I mean, you could be coming up with models of health outcomes for health interventions or financial models, and you want to predict expenditures or revenues. Voting outcome, I'm a dual citizen, so the recent US election, there was some professor who had a foolproof model of the voting outcome, and unfortunately his calibration didn't work this time, but that's a model. And then there's data. So from a basic science perspective, data is what is measured on a real world system. That could be a system of equipment, which we're talking about. It could be a system of people, and so on. One of the basics of data is its measurements or observations of real world systems. So one of the important aspects of terminology. So data is not just any number that, say, shows up in a computer. You cannot have data for the future. A very obvious point, but I've heard that used by colleagues and professionals. For example, it's like, well, my data for this building in 2026 is blah, blah, blah. Well, that's a different meaning of data. You can't measure the building in 2026. We're not there yet in time. And the whole purpose of science is to compare real world systems to models, which we're going to do in our case studies coming up. And by success, we want to, how well does our data compare with predictions? We're going to talk about that too with option D. And of course, we use data to build models, right? Regression models have data from some other system as an input. All these physics equations like Q equals mass times specific heat times change in temperature. Ultimately, those equations came from somebody doing measurements of temperatures and heat, and they figured out that this equation fit certain processes, right? All right, so as I mentioned I'm going to expand a little bit in the introduction that there are two types of models used in M&V, or two types of models used in M&V. The first type is the one that we're talking about with option D, which are these engineering science or physics-based models. There's just a couple of equations there. One is a Bernoulli equation for fluids. The other is the first law of thermodynamics. These are the types of equations that are in those computer simulation models. They're often used for, when do you use these models? Well, new construction projects or when baseline data are not available. It tends to be more expensive and you need to justify the cost. Those are two basic attributes of option D, M, and V. There are also statistical models of that form, and these are typically not what are used in option D, although I wouldn't rule out that maybe there's some regression model you could build for some industrial process and then apply it to some new process that you forecast. But usually it's not. Usually it's number one there, just to be, let's say, abundantly clear. And again, what are data? Data are observations of real world systems. Examples, you measure electricity from a building submeter. You measure the number of hours of a lighting system using an on-off logger. It could be, just to throw in some example, some work I did for City of Edmonton or some I did for Atrium Healthcare. You can use like transactions can be data that you may actually put into an energy model, which I've done, for example. Forecast are estimates of parameters using models for future. It's not possible to have data using the basic science definition of data. You cannot have data for future events, period. And I think it's helpful to be clear with terminology. So if we're talking about data, this is what it's: measurements and observations of real world systems, and that can be equipment or people. Estimates is a little more general, or parameters calculated using models. They could be estimates kind of how existing processes past have worked, or they could be used for forecasting. Okay, here's another concrete example of data. These are two projects. These are actually utility bills for natural gas consumption. Only one is real data. And how would you find out? Maybe I'll just pause here if anybody wants to put anything in the chat, or just unmute yourself and suggest an idea. So one of these is definitely not from a meter. And how would you figure that out? If there's any ideas. No ideas? That's okay. Well, let's just carry on. So the ATCO gas bill, this is just what I did. I made a regression model of gigajoules versus heating degree days. And the model just fit like exactly, like perfect fit. And so that just seemed too good to be true. It was like there was almost essentially no error. What that means now, what that means is that those numbers came out of a model. They didn't come from a meter. And so I wrote to ATCO Gas, and this is the actual response I got. So this is kind of practical advice if you're an M&V professional. One thing you can do is just, where did these numbers come from? Well, let me contact that person, that organization, right? These numbers came from ATCO Gas. So they responded. They said, yeah, we read low and medium use sites on a monthly basis. So these are daily data. So these are January 1st, 2nd, 3rd, right? Notice these are daily numbers. Well, you cannot get daily numbers if the meter is only read on a monthly basis. And what the utility would do, if it's a higher consumption account of 8,000 gigajoules per year, they would read it on a daily basis because they need that for a demand charge. So long and short is, it was very clear this is not a high consuming site. It's much less than 8,000 gigajoules. Plus the fact that it fit, the regression model was just too perfect. So very clearly, these were estimated numbers in the bill, these daily numbers. So for me to treat those as metered daily numbers would be wrong. And then the Piedmont gas bill, I wrote to them. I mean, I didn't have any questions, or at least I guess I did have a question because I actually wrote, and this is exactly what I got. They said, yeah, they read their things they have automatic meter reading, and they read them daily, and everything lined up. What they were telling me lined up with how I analyze the numbers. So I trust these are actual meter data for January 1st, January 2nd, January 3rd, and so on. So the lesson here is, again, most of us, I would say most professionals, by default, we're going to get utility bills and assume that's metered. It's not always the case. All right, so when to use option D, the basic idea is here. When your baseline energy data does not exist. So there are two cases where that would be. You have a retrofit or an existing system, and the baseline is just not metered for whatever reason. That's there was an industrial furnace project I'm working on or worked on, and the old equipment just did not have much metering installed. So it had a few temperatures and things, but no fuel consumption was metered, and that is very common. The other common situation is new construction, where it's literally impossible, right? The less efficient industrial plant that did not exist, you cannot make a measurement on that plant. Somewhere, I have another Menti question coming up. Okay, so this is the basic IPMVP. Well, it's not limited to IPMVP. Say ASHRAE 14 and everything will follow the same idea. So this is a classic M&V chart to explain what are savings and illustrate that. So you have a baseline or pre-retrofit system. There's some implementation period where on a retrofit, equipment is installed, operating practices are changed. And then the green line shows post-retrofit or reporting period consumption. And then there's an adjusted baseline because you want to compare baseline and your reporting period on the same basis of, say, production rate, product quality, metrics, and so on. So you may do baseline adjustments if production rates change or product mix would change in an industrial plant. So for further on that, those first 3 webinars that I mentioned, there's a little more detail on these basics. And with option D, that adjusted baseline will come from a computer simulation model. That's the usual situation for option D. So some unique issues with industrial option D is there's a wide variety of processes. They require specialized process knowledge. You require specialized modeling tools and expertise, and you require some M&V expertise. And it's very common, it's pretty rare in my experience that you get the process knowledge, the modeling expertise, and the M&V in one person, or even necessarily one organization. Like the little icons there's sort of 3 roles that are critical, and rarely does one person or even one organization, is less common in my experience. And just to reinforce what I mean by different types of processes, I have a survey for you back using the same Menti tool. So if you go to menti.com, and again, I'll just put it in the chat. If you can answer this survey, 528-1411. So just go through and check off of these different processes, pulp refiner, lime kiln, cement kiln, weaving machine. I'd like to see, just check off which processes you're even heard of or been involved with a project. Okay, we got 13 responses. Hopefully we can get a few more. So while people are responding, I do remind, we do have 1.5 hours for this webinar. So we're going to finish up in 20-30 minutes and still have some time for Q&A, I think. So We got 16 responses. Maybe a few more. Well, 18 responses. Okay, fair enough. I mean, I didn't know how this was going to come out. I didn't know if we'd have some of these, if there would be anybody, like especially walking beam furnace, which I came across on one project, a weaving machine, full air separation liquid. So there's, somebody has some experience with some of these rare processes. The other key idea here, this list could be, we could have easily hundreds more of these types of processes, maybe more than hundreds. And one of the key messages, I'll just plunk this in the chat one of the key ideas is that there is no such thing as an industrial expert from the standpoint of nobody has expertise in all these processes, right? There's some basics that people can figure out for many of those, but yeah, there are experts for every one of these. There are people who have direct experience, engineers and other professionals. So it's important to keep in mind, and my point is, find the right expertise for your process that's involved. Don't just assume me or anybody else, for that matter, is, well, if they're an industrial expert, they should be able to know the intricacies of a walking beam furnace, or depending how critical that knowledge might be. Okay. So here are just a sample of simulation software examples for pipeline simulators, for chemical processes, pipe flow, Schlumberger's model used for things like compressors. There's pulp and paper models. There's HYSYS is a general like mechanical process simulator. And the list could go on. These are just examples. So just want to be really clear when we're talking about simulation software, it's these types of things. It's usually not just a spreadsheet, although in some cases it could be. It's usually not just a regression model. It's usually some sort of more specific simulation tool, such as these examples. Now, if we were talking about buildings and not industrial processes, there would be some of these, IE4 or, there's a lot of specialized modeling softwares for buildings, but we're talking about industrial applications here. So this is straight from the IPMVP about model calibration and in the 7 steps. So this is literally right out of the IPMVP. I did actually help co-author the option D material that's in the IPMVP core concepts, along with Leah Webster, who is the lead author of the core concepts. And so anyway, since I helped write it, obviously I agree with these steps. I'll just highlight, so this is a little checklist that you can ask to be followed if you're involved with an option D project for industrial. Confirm assumptions and documentation. I'll just mention a few of these things, which hopefully are kind of obvious, but it helps to have them laid out. You want to gather data, run your models, compare the simulation model to the metered energy. I guess reality check those parameters to confirm that they represent actual operation. Don't just believe the numbers. Evaluate the consistency and the acceptability by looking at whatever might be involved. Calibration data, production versus whatever variable that would be a key driver of production. Look at changes over time. And it's usually iterative. And ultimately, you're looking to revise the model inputs and assumptions to bring your predicted results within agreement of your model. So I have one last Menti question to ask you, because the IPMVP nor ASHRAE 14 for example, M&V, they do not prescribe what is a reasonable or acceptable agreement between model and data for your facility or your system. So my last question, well, that's almost my last question. So I'm curious, what is your opinion? So what do you think is a reasonable % accuracy or agreement between a simulation model and actual facility or system energy consumption data? 10%. Done. Okay. More opinions. 15. 20. Okay. 5. 40. Yeah. Okay. 0. I like 0. I don't know how practical that is. Good. Okay, 22 responses. Yeah, so yeah, or look at percentage of savings. So again, there's no correct answer, if you will, from the standpoint that the standards. I mean, I usually go with it really depends on the project, and that really is the best answer. You really need to think about that in terms of go back to that checklist, like what are the objectives of the project? Who's the lead M&V professional? What are the results of the M&V going to be used for? Probably some financial transaction, and all those factors, it gets to be a judgment call. You know, in general for industrial, I found that 5% works. I've cited, there's another M&V standard called FEMP, Federal Energy Management Program in the US. So it's usually used for buildings, not industrial, but it does provide some guidance on what agreement there should be between model and data. Okay, so I did have just one more thing here, and then we'll get into the case studies. So what it comes down to, the IPMVP option D savings calculations, is your energy savings is the difference between your baseline period energy from the calibrated model updated to baseline conditions minus your reporting period energy from the calibrated model. So keep this equation in mind. I guess and we'll do one last question for you, which is this one. So Menti limits the number of characters you can use, so I have to keep it short. But you have a new plant model that predicts 100,000 megawatt hours per year consumption. It's electricity, but it could be any energy. What is measured is 95,000 megawatt hours per year. Your hypothetical baseline model of the inefficient plant that was never built predicts 120,000 megawatt hour per year. So what would be your option D M&V savings? Fifteen responses. Okay, we're up to 20. I'll just tell you, and this will be, the correct answer is actually 20,000. Okay, because it's the difference between your baseline model of 120,000 and your calibrated model of the new plant. Emphasize the word calibrated model, which is 100,000. So the difference is 20,000, and that would be your IPMVP savings. That is exactly what this equation says, which is straight out of the core concepts. All right, let's just roll into our case studies. Okay, so first case study is an oil pipeline where it was an existing system and more efficient pumps, variable speed controls, more efficient motor, more efficient transformers were put in. And these are more efficient than the baseline. For example, 75% pump efficiency on average versus about 60 for the baseline old pumps. Motors improved about 1.5 percentage points and so on. So the methodology, so the baseline system never they had to simulate because they did some expansion and they didn't install the less efficient on the new production. So there's a little bit of a nuance there, but they didn't have the opportunity to measure the baseline at the production rates with the less efficient design features. So that had to be modeled. And so what it comes down to is this diagram just shows your typical pump-driven system where you have a power supply with a transformer and a VFD there and a motor, and you might have some connection between the output of the motor shaft and the input shaft of your pump. And so hydraulics were modeled with a commercial hydraulic software, which estimated pump shaft energy, like here. I guess I can highlight stuff, okay? And then there was some spreadsheet calculations which converted shaft power to electric power based on the efficiency of these motors and drives. And so the results of this, using realistic but not actual numbers, were that the actual electricity consumption was 102,500 megawatt hour per year. So that was actually what was metered. So this just illustrates the steps of an option D. So a model was built of the high efficiency as-built system, and that model predicted 106,600 megawatt hour per year. All right, so this is very typical option D, just to get in your mind the process. So you have the actual efficient system where you meter consumption. And then you have a specialist supported with a process expert to build some sort of simulation model for the as-built system. And the difference between the model and the meter was, in this case, 4,100 megawatt hours per year. So then what happens is you take that same model and you modify it with the standard or low efficiency design features, and you simulate the less efficient equipment that was never installed. And then you, so this was for a plant expansion process. And so the baseline never existed. It was not expanded with the low efficiency equipment, only with the high efficiency. And so the model predicted 139,000 megawatt hour per year. And so I'll just jump to this bottom equation here. So if you look at the IPMVP equation 10, which is the same equation a couple slides back, the savings is the modeled, the baseline model prediction for the hypothetical inefficient baseline, 139,000, minus what the calibrated model result for the as-built system. So that number came out to 32,400. Now it seems a little counterintuitive or perhaps even wrong to just compare the model to model. Like, where does the calibration error come in? Well, where it comes in is what I'm highlighting. I'll do it in a different color, I guess in green, is you can calculate that a different way, which is take your baseline model minus your actual consumption and adjust it for the calibration error, and you get the same result. So that little calculation is very central to IPMVP option D. And just to state the obvious here, why is there no calibration error for the baseline? Anybody? Or
Because
put it
there
in
is
the
no
chat.
baseline.
There is no
Wasn't measured.
baseline. Yeah, thank you. You cannot calibrate to the system that never existed. Just like a new building, right? Nobody builds the less efficient building without heat recovery and low efficiency devices and calibrates the model to that and compares it to your as-built efficient building, right? It's crazy, right? So yeah, the reality is there's nothing you can do. You can't calibrate the model of the baseline directly. What you do is you build up confidence in the model and the modelers by calibrating the model of the actual process. So that is a critical step to build. I like to think of it, gain confidence and trust in that. Think of that 3-person team. You have an M&V professional, you have a modeling expert, and you have a process expert. And maybe a couple of those are in one body, but maybe 3 different people or even more are involved. But you have to build the confidence in that ability to model and calibrate the as-built process. And then you just have to trust, because we have no choice, that model of the hypothetical baseline is accurate as it would have been if the facility had been built or the system had been built. Yeah. So that is a really key concept and a really critical task in option D.
I think, Eric, you have a question, a raised hand.
Oh, yeah. I was going to
Mohammed,
pause.
if you want
Thanks.
to unmute yourself.
Yeah, go ahead. Yeah, because we're going to move on to the next case study, but we have plenty of time.
Yeah, can you hear me well?
Good, I can, yeah.
Yeah, thanks, Eric. So I wonder what would be the value of evaluating the savings this way if you don't have a baseline? Usually you would have a less efficient system and you want to evaluate the savings for a potential upgrade, and you would do it in that direction. But I'm seeing this going in the opposite direction. So what is the value of having the savings calculated this way?
Well, I would say the value is it's the only way it can be done, because if you have, in this case, a plant expansion, you cannot, you need to come up with a number for the energy consumption that would have occurred if the less efficient equipment had been installed. And so there's 2 ways to come up with that number. One, you could build the inefficient plant and measure it, or, which of course is crazy expensive and unrealistic, or you model it with some simulation software or some other model.
Oh,
there really is no other way. Yeah, there's
so
really
it is actually a comparison between 2 different potential systems, one less efficient and one more efficient. Both are hypothetical. And
no, both are not hypothetical. The as-built system is something you can put a meter on, and then you model. So just to be clear, the expanded plant in this case built a model of the as-built system with these efficiencies in it. I mean, these are made up, they're approximate, but they're very, with the variable speed control, the actual pump curves, the actual motor efficiency data that you get from manufacturer and transformer. So a model was built of the system as it was built at the actual production rate and product mix. And that model was calibrated to match the metered consumption of the pumps and the pump motors. So that's the first step in option D. And so that builds that modeling and process expertise. And you want to calibrate that model to some agreed upon number, which I tend to use 5%, but you could use a different number depending on your project circumstances. Then the next step is, okay, what would have been the electricity consumption if the plant expansion had been with these efficiencies that I'm highlighting here in green. And that can only be done with a model. Like, you're not going to, I mean, there are other things one can do in general. You could find similar processes with those efficiencies and maybe do some measurements there, but that's not on the same system that was built. But yeah.
Thank you.
So yeah, that's the crux of it. It's kind of simple and a little bit counterintuitive sometimes. And maybe I'll just back up very briefly. This equation about using the calibrated model versus calibrated model, that, even when I made mistakes, I readily admit. When I first started doing option D, I was doing it wrong, or at least interpreting it wrong, because I was using calibrated model minus the actual consumption, which many of you answered in the Menti survey. But that calculation ignores the model error of the modeling error of the as-built equipment.
Mm-hmm. I think
Okay.
next we have a question from Josh as well.
Oh yeah, go ahead, please. Go ahead,
Josh, you
John.
have a
Sorry.
raised hand. Go for it.
Yeah, sorry. Just a comment. There's a few questions in Q&A, or I had put one in there because I don't have access to chat.
Oh, okay.
And then my second question, you just answered, Eric. So yeah, thank you. I now understand why the post retrofit case is modeled instead of just using the as-built data. A mistake
Sure.
I would have made.
Yeah, no, I've made it. I don't mind admitting it's the truth. The chat question, sorry, the Q&A. Sorry, Melis, how do I
So I
see
think,
those?
yeah, I think Josh had put a question in there, and I think that's the one he said you answered. So I'm just
Okay.
gonna mark it
All right.
as closed for
Okay.
now. I'm checking the Q&A for you.
Okay.
So if we have anything coming through, I will let you know.
Okay.
So far almost everyone is in the chat, and I think there's Z3. I don't know who that is exactly, but you have a raised hand and some comments in the chat. I don't know if you want to speak
Oh,
or if
sure.
you just want me to read your comment.
Yeah, I see. No, I see. So why not submeter and monitor all loads, especially for baseline data? That's a question by someone Z3. You could do that. I mean, that comes back to, that's a judgment call. How much process loads are you going to meter in the as-built system? I mean, that's just, so you could submeter all loads, but keep in mind, like I'm going to do one for case study number 3 coming up is for a natural gas processing plant. And it's very common you have big motors like 4,500 horsepower or 33,000 horsepower, big motors. And do you meter everything? Are you saying, well, would you meter the 5 horsepower motors on some small pump? Would you meter those too? Maybe, maybe not. You might just have a judgment call about the cost of the M&V versus the benefit of metering absolutely all the loads. So yeah, there's no prescriptive guidance. It is a matter of using judgment, going through those steps that I introduced, like what are the project objectives? As I covered in other M&V webinars, a big part of who are the stakeholders that are involved. So if the project is funded through a loan or a subsidy from a utility or a government agency that's giving a grant, a rebate, financial capital incentive, they may have requirements about how accurate and so on. I mean, IESO and Save On program that sponsored this, that's exactly how they work, right? They're incentivizing their industrial customers. So they, as a stakeholder in the project, will have some input on, as part of the collective judgment about what is an appropriate level of metering. All right, so this is a different kind of system, very interesting. So this was an expansion of an existing wastewater treatment plant where new water treatment modules and membranes were added. The baseline is that would have been a pumped design. And in the design of it, they were able to eliminate the pumps and use gravity and siphon to eliminate the pumps. And there was a requirement for some compressed air injectors, which was a small power consumption. So that's the project. This is a schematic of the process, which the details are not within my expertise, to be honest. But basically, there was an expansion where there was a siphoning was enabled and the use of gravity, which cost extra capital dollars in the investment, but it literally eliminated the requirement for pumps to push the water through these membranes. And so it was option D because the pumps were never existed. They didn't do the plant expansion, install pumps, measure it, and then move equipment around to eliminate the pumps, right? That's crazy. So the pump energy for the reporting period was 0. It was unmetered because they didn't exist. And there were some small new electric loads for these injectors, they were called. So those were done with spot readings because they were really small. And the baseline simulation took the actual fluid flows and pressure differences, which were overcome through siphoning and gravity instead of a pump. And so you could say like the head was metered, the fluid head was metered, and then the electric power was calculated using assumed motor and pump efficiencies. So we didn't need a sophisticated software to do this. I did this myself. You just use basic pump equations about the fluid power divided by your electric and pump losses effectively. And so yeah, we calculated the fluid power based on metered flow volumes and the pump head based on measured pressure losses. We used just standard fluid equations that I learned as an undergraduate a long time ago. And these are the results. So we had so the post-retrofit power was just about 20 kilowatt for those injectors, but the pump energy was 0. And then the savings were the simulated power consumption of the pumps that were never required, less these new injectors that were required to make this siphoning gravity system work. And that was the M&V. So I'll pause if there's any questions on that. Josh?
Yeah, could in this case you conclude that the baseline model was actually calibrated to the post-retrofit conditions?
Yeah, nice to have you here, Josh. And good question. I didn't do any that's a great question. How do you calibrate your reporting period if it's 0? So I guess it's inherently calibrated. A model of, build a model of no pumps, it's 0. So yeah, there was no model calibration that was possible.
But for the
reporting period.
baseline, you actually used parameters from the post-retrofit case, like pressure, flow rates.
Yes.
So you were effectively adjusting your baseline model or calibrating it?
Well, think of it, it's the same fluid power was being delivered by the siphon gravity system as would have been delivered by pumps, the same fluid power. Yeah, so we effectively measured the fluid power delivered by the siphon gravity system. And then we said, well, how much electricity would it have taken to deliver that same fluid power on like an hour by hour basis? I think it ended up being, or it might have been 15-minute even. Does that make sense?
Yeah, thank you.
Yeah. But you're right. There's no way to calibrate the as-built system. I mean, if it had been big pumps, it would have been the baseline, and small pumps is what was built. You could build a model of the as-built system and calibrate it, but when there's no pumps. And this is not the only project. I've seen natural gas gathering systems where bigger pipes and other design features were implemented so that you eliminated field compression. So your reporting period compressor power was 0. So the third
you
and
have
final.
a couple more questions.
Oh, okay. Yeah,
Eric.
sorry.
Yeah, you have Mohammed first.
Yes,
Great.
thanks. So just a quick question. So the savings were calculated as the difference between the baseline that was modeled using the fluid mechanics equations
Yes.
and okay, what was on the post or like the
Yeah,
injector's case, like what was there?
yeah, that's 20 kilowatt. That was just some small, it used some compressed air in the system. I can't at the moment remember exactly why that was required, but it was. So the reporting period power and energy is the sum of, you could say, the pumping power required, which was 0, and these injectors, which would have not been required in the baseline system.
And these were obtained from measurements or from calculations?
The post retrofit from measurements.
So in this case, like I'm curious to learn, like at the standpoint of like option D, does it have to be calibrated model minus calibrated model, or can it be a mix and match if the
Well,
case allows?
yeah, it's technically, I would have to, I guess, argue it's a calibrated model of the pumps, because I can argue that, but it's really a philosophical point. There's no pumps, so my modeled consumption of 0 has to be correct.
No, I agree with you, but like,
Yeah.
does option D require us to use a similar calculation as you did with the pumps on the injector's case, so that we're like basically
Well, it's not that
leveling the?
prescriptive. Yeah,
Okay.
that's a good question. I mean, the IPMVP core concepts, and I would say the same for ASHRAE 14, 2023, which is another commonly used M&V protocol. They're not that prescriptive in general, especially the
I know.
IPMVP. You know, there
Agree.
are certain principles, like EVO and the IPMVP say, well, you actually have to make some measurements on your as-built system if you want to call it M&V. Otherwise, it's stipulated savings and it's really not doing M&V. I mean, you know, they do have some limits, but it's generally guidance, and it's up to the M&V professional to interpret. But I mean, in my interpretation, this is the best and only practical way to adhere to the IPMVP option D requirements. I mean, I'm always open to, like, what else could we have done, right?
No,
And is it
I totally agree. It's
Yeah. No,
like
no, it's
I've
fair.
been there, but like some evaluators can argue against that, and like they go by the book and they say no, like it has to be the same kind of level of comparison. If it is model, it has to be model
Sure.
on the other side. You know,
Yeah.
I totally agree with you.
Yeah,
It's
no,
like what
I
else can be
wear
done?
the impact evaluator hat sometimes. I've done some projects, but yeah, and that's fair. I mean, you have the discussion, the debate. I mean, what can an evaluator say here? Like, if someone wants to reject the results, fair enough. Just why and what could have been done differently?
Spot
is
on.
it
Yeah.
fair to say, Eric, that the reason that it looks like we're not comparing apples to apples is because we're kind of summing up two systems, one which is your pumps, which has a calibrated model and a consumption of 0 in the post, and the other system is like non-existent in pre and then measured in post.
Well, I guess the argument can be made, but fundamentally, we're just talking about there was the baseline system that could have very well been built, which would have had pumps without injectors, and that pump could have been measured. You know, the pump motor power could have been measured, but it wasn't built. So the best thing we can do is estimate it using Bernoulli and basic fluid mechanics. And then for the as-built system, the electricity consumption comprised entirely of these injectors. So it's definitely following the method, in my professional opinion, and there's no better way to do it. We measured everything feasible. We did measure the pressure, the flows, and the pressure losses across the membranes were based on metered data. That, you know, it's as robust as you can get given the circumstances, and it fits within the protocol in my assessment. So, you know, but you know, this is exactly, you know, it's fair to be challenged. I get challenged all the time, and that's totally fair. Especially in M&V, if parties involved don't like your results, if the savings are too low or appear too high in their opinion, and that I get both, you know, I've got both sides of that. And then you debate and say what could be done differently. And sometimes I admit I'm wrong, and so be it. That's part of M&V.
I think you have one last question. There's a raised
Salah?
hand from Salah.
Salah,
Hi.
yes.
Hi,
My good
hi,
colleague.
Eric.
Good, go ahead. What you got?
With a good question. This data metered volume and the pressure, was that collected over a full year period, right? I just want to know that.
Good question. I think it was a year. I don't remember. Sometimes it's in industrial plants, the basic question is how seasonal is the operation? And often the answer is not. So in industrial, it's not always necessary to get a full 12 months. I'm pretty sure this was a long time ago, like a decade ago. I'm pretty sure we actually did have 12 months. But the key, the key question, Salah, is what is the appropriate minimum duration of the reporting period? Now, for buildings and HVAC processes, because they are almost always based on outdoor air temperature is critical, you really need to do 12 months to capture all seasonal and shoulder season effects. In industrial operations, many of them are not seasonal at all, or negligible, small enough to be ignored. So sometimes in industrial, you can get, weeks of data might be sufficient. And that's a judgment of M&V, of the cost of M&V versus the value of the, what you get out of the M&V. That was covered in the other webinars.
Thank you, Eric. That makes sense.
Great question. So the last case study is this natural gas plant. So this is just a typical, although it is roughly typical, all the designs have different configurations, but you have a lot of compression of feed gas, and then you have vapor recovery and refrigeration to drop out the hydrocarbon liquids and things like that. And so these are not all of the energy efficiency measures, but just a sample of them, which is so this was a newly constructed plant, and so it had feed gas compressors where in the baseline it would have been built with single speed and recirculation is the assumption for some of these big motors. These motors, you can see like 31,400 horsepower motor. That's not an off-the-shelf motor. That's nothing you can find, a NEMA standard on, for example. And the baseline would have been the least cost, technically viable custom motor. But of course, the plant owner could invest in a higher efficiency synchronous motor, with squeezing out an extra 1% efficiency or something like that, or even a 0.5% is very significant when you're talking, say, 25 megawatt motor. Larger diameter pipes versus smaller diameter that would have been feasible to meet pipeline velocity requirements. So these are the measures. So it's a partial list. There were more. So why is it option D? Because the baseline system and those baseline inefficiencies never existed. You have to use simulation. In this case, it was a Schlumberger software that was used to estimate shaft power of the compressors. And those shaft power numbers were converted to electric power numbers using a spreadsheet analysis. It was based on a full year of actual production and energy data. And savings were determined for individual measures. Take into account things like VFD efficiencies, which I'm showing there on the right. So this is just a sample of the type of modeling. This comes out of a Schlumberger model. And so it's the same process that we've talked about with the oil pipeline and effectively with the water treatment. So what do is you take the as-built plant, you build a model of it, and you calibrate that model until it agrees with the metered consumption, both in total and for some individual major motors, such as the 31,000 horsepower motor. And then there is a targeted agreement, a targeted calibration error of, I think we went with 5% in this project. It might have, 5%. So you build the model of the as-built, as-operating plant, calibrate it, And then the same model, which I'm showing you here, gets altered. So instead of VFD control, which was actually installed, you simulate recirculation and valve control. You change the motor efficiencies from 0.95 to 0.96, things like that. You eliminate the VFD losses do not exist in the baseline model. So whatever, if the compressor efficiencies change, then you change those in your baseline model. And then you come up with the same type of thing. You come up with your modeled actual power, you compare it to your metered actual power, then you model your baseline, and then your power savings are the difference between the calibrated model of the actual power and the modeled baseline power. And then you multiply by operating hours, and it's usually done in like a data bin format. So this would have had like 3 data bins for measure 1. So that means you take the actual operating data, and then the analysts doing the modeling and the M&V engineer will make judgments about, okay, how do I bin this data? Am I going to run a simulation model for 8760 hours? Well, probably not, because that's very expensive. So you're going to take, let's say, your 8760 hours, and in this case, it was decided, well, you know what? There's 3 bins of data where the process variation is very close. So that's what we mean by a bin analysis. You put the data into bins, you model each bin, you compare it to actual power, you calibrate it till you get close enough, then you model your baseline, and then you get your savings bin by bin, and you sum them up and you get the savings for that measure. So any questions on that? Mohammed, go ahead.
Yeah, like one quick one, and then maybe another one that might be unrelated, but does it have to sum up to 8760 hours, or this is the actual operating hours? I see 8548.
Yeah, it was the actual operating hours. So it's 8760 hours of calendar time. It worked out to 8548 hours of operating time. I think
there will be some downtimes.
Yeah.
Okay. So like my second question is on, I heard you mentioning measure level savings were calculated in this project, and it's kind of tricky for me how measure level savings can be obtained from these types of models because of interactive effects. Did you face any concerns with interactive effects between the different measures in the same package?
Yeah, interactive effects do need to be taken into account. Absolutely. That's right.
And may I ask how you did that here? Like, what approach did you use?
Yeah. I don't know if I have a. So just to be clear, I was not the M&V engineer for this. I was reviewing the M&V. But so for example, when you have like the motor and VFD connected, well, like the pipeline. So you really kind of need to do these in sequence. It's called like the stacking effect. So when you analyze your savings, what you might do, for example, is model the effect of the efficient motor, and then you use that as kind of your new baseline, and then you model the effect of the going from single speed to variable speed control. And by doing that, you're capturing the interactive effect of a more efficient motor with the conversion from single speed to variable speed.
Yep. So
those,
and the cascading effect.
Yeah, exactly. So it's called, it's actually in the only standard or guideline I know where it's mentioned is the ASHRAE Energy Audit 211 standard, I think mentions it. And then the ASHRAE Commercial Audits for Buildings book, which is outdated, and ASHRAE keeps saying they're going to update it, and it hasn't happened yet. But it talks about multi-measure stacking effects. That's the phrase. And it's the same applies here where, so the savings for the pipe, let me just say this, the savings for the larger diameter pipeline and the more efficient motor and the conversion from single speed to variable speed were all measured. For example, most of those savings were realized on one motor. So you do have to be very careful about interactive and stacking effects of high efficiency motor, pipeline diameter, and the speed control. So you do have to consider the interactive effects, and you might just model it in sequence. And if you're familiar with doing this, the really simple example is, let's say I convert the office I'm in, the lighting system, and I put in new efficient luminaires and I put in lighting controls. Well, if the luminaires are 50% more efficient or half the power and the operating time is cut in half, well, the total power consumption savings is not going to be 50% plus 50%, right? It's not going to be 100%. It's going to be, well, I'm going to model that I take my lighting luminaire savings first, and then I save that as my new baseline, and then how much do I save with the controls, or do it the other way around. It's the same logic with these.
And I can add one more complexity to that, like fuel switching your heating system from fossil to electricity. And then you'd need to account for the effect of the lighting efficiency improvement on your natural gas on the baseline and electricity on the upgrade.
Well,
so much fun there.
Yeah, so that is another kind of, that's a classic interactive effect from M&V. So that's the type of effect you'll read about in the core concepts. Interactive effect is also used for that multi-measure stacking effect that I mentioned.
Got it. Thank you.
It's really two specific meanings for this term interactive effect. Okay, so we're really just about done here. So one thing I'll say, and this is to just have some discussion. So there's been a lot of projects I've been involved with say these natural gas plants. I'm here in British Columbia. There's a lot of that activity. And the long and short is there's multiple parties involved, and there's been some serious disputes about how accurate are these models, especially for single speed motor control with recirculation on, say, big motors like 4,500 horsepower, 33,000 horsepower, and so on. And the disputes are in the range of, say, something like 40%. So, but so let's just say you're involved. This is exactly a situation I've been involved in. And these are big numbers. Like the cumulative savings across multiple projects is on the order of 500 gigawatt hours per year, like almost 1% of all the utility consumption in this jurisdiction. It's just a big number, and it's important is the key idea. So my question for all of you, so if you have a discrepancy, like you have multiple parties who say, like one party, the modeler might say, well, this is the baseline power would have been 25 megawatts. Let's just say that. Other parties involved who are quite credible, like the evaluator, somebody mentioned the evaluation. Maybe the evaluator says the model power is not 25 megawatts, it's more like 20. And they come up with some other analysis approach, differences of technical opinion from, let's say, qualified people. So how can that be resolved? Is my question to any of you. Like, what would you do? Salah, go ahead.
I think this has to be set up front at the very beginning in the M&V plan. That has to be agreed by the customer and the consultants. If it's set in the M&V plan, then nobody can dispute that down the road.
Yeah, good point. Very critical. Thank you. So the modeling method, who's doing the modeling, the calibration error, all those need to be set in the M&V plan. And if that happens, it should be indisputable. Well, in effect, that was done and people still disputed it. So, but your point is well taken.
I would say it all comes down to like a robust calibration approach that everyone agrees to, because at the end of the day, these are all models, and without proper calibration and validation of these models, like
Yeah.
garbage in, garbage out. So it has
Yeah.
to be a unified calibration approach that everyone agrees to, and whatever savings comes out of this approach, it's taken for granted. I would
Yeah.
say also post EMNV type analytics as well. Like once an upgrade is installed, you do a pre and post measurement to validate your savings calculated through
Yeah.
the modeling approach. Like it has to be like a suite of solutions, but at
Right.
the end, it's consensus between all involved
Yeah.
parties on a calibration framework that everyone agrees to.
Yeah, no, I agree with all of that. Yeah. And having said that, we still had some disputes here, but yeah, I agree 100% with what was just said. Absolutely. Salah, did you have more comment, or was that your hand?
Just quickly, if you sub-meter that motor, okay, which has the VFD on it,
Yes.
okay, sub-meter, and then you just basically disable the VFD for a short period of time and mimic that in the model and see if you get
Yeah.
the results.
That's a great, excellent. Yeah. So yes, that has happened. The problem is the operating modes of most interest are at partial production flow, and we haven't had, there's no operation that's willing to or has the capability to operate with single speed and recirculation at a low flow turn down, a lower flow turn down. Routinely, the VFD will be effectively shut off or bypassed when the compressor is at essentially 100% because you don't need it. But you're getting to the point. What the approach I've taken, which would work if it were feasible, but it's so far not feasible, is to say, well, let's just find some natural gas compressors which are electric driven with single speed motor and recirculation control, and get some measurements on those systems. Even if it's not the same system, at least build confidence in the ability to model that type of specific control mode. And unfortunately, we've not been able to make that happen because there is no operation that has been identified where they actually operate single speed electric driven motor with single speed and recirculation. They always use VFD for those that can be identified so far. But yeah, Salah, I agree 100%. You can maybe take your actual system. I mean, that would be more like an on-off. It reminds me, there is something called an on-off method in M&V. I think it's briefly mentioned in the IPMVP. There's an ISO M&V standard that is more explicit with an on-off control M&V. And what that means is sometimes in M&V, you can turn off the efficiency measure or bypass it. And Salah, you're referring to that, I think, effectively with this to say, well, what if we just turn off the VFD and operate it in simulated how it would, that they would have to do a valve control and recirculation. Well, we haven't found any operation that's been able or willing to do that. But that is definitely a valid and common M&V method. So good point. Yeah. Josh, I see your hand up.
Yeah, I guess a philosophical question. If the theoretical base case is something that would never be implemented in the real world or isn't standard practice, why would you be modeling that base case in the first place?
That's the 500 gigawatt hour question, Josh, that's being answered with the study. It's like, well, if we cannot find the inefficient baseline equipment anywhere, I mean, should it be incentivized in the first place? Like, why are we doing this thing? Very good question. So yeah, that question is being addressed through a survey and study. Yeah, why is it even a valid baseline? I think is what you're saying, but and that question has been asked. Yeah. And that question's being addressed. Now that's a little different than the M&V, and this is actually a very good point for M&V because often as the M&V professional, those decisions are made by others. That applies even to buildings. What is a reasonable baseline building, right? That would have been acceptable per prevalent codes and things like that. that same question comes up in industrial or even buildings. Like what is a valid hypothetical baseline based on the common practices and or applicable, let's say, codes or regulations that might apply? And there's lots of arguments or disputes over that. And usually the best way to, well, one way to, let's say, reduce the uncertainties there is to say, well, let's just go find some inefficient system, whatever it is, like with water treatment. Let's just go find some similar water treatment processes that are pumped, and you could do some measurements on that process and model it. And then you can use that activity to, let's say, inform what you would have done on the actual system that's undergoing M&V if there were questions. Same for natural gas. Well, let's just find some systems that work like this with single speed motor and recirculation control, even if it's not the same process we're interested in. If we can get data and modeling done on a similar process, we can build confidence in doing that same estimate for the process we are interested in. But if you cannot find that inefficient baseline system in the first place, then you can't do it. So just move on to key issues in summary. So the word is heterogeneity. So there's a wide variety of industrial processes, small local manufacturing plants to large complex operations like pulp mills and so on. As I mentioned, you really need specialized process knowledge. Often the process specialist has limited M&V knowledge or training, or vice versa. And I've been involved in this. It happens. Some people, I've come across highly credible experts who have tremendous process knowledge, who sometimes come up with the most incorrect baseline assumptions from an M&V perspective. So it really takes both expertise as well as simulation model expertise. Even some of the modelers who have done this kind of modeling, believe it or not, the person actually running the software really is not the process expert. They're getting guidance from another engineer who has more of the process expertise, which perhaps is not ideal, but that's just the way it worked out. I mean, the person's familiar with it, but in the discussions and things, it was very clear they didn't have a lot of field experience, which is not an insurmountable problem. But from a project perspective, you want to make sure you have someone with that field experience, design experience, whatever level of process expertise is judged to be critical. You want to bring that expertise to the project. It doesn't necessarily have to reside with the modeler or with the M&V designated professional. Yeah, so other key issues, I mean, metering is critical, just like we had some discussions. Which loads do you meter? Do you try and meter absolutely everything, or do you make strategic judgments based on cost and accuracy that only the largest loads? What that calibration error and model validation process, I think that came up. There was some great points made by some of you folks that really ideally put that in an M&V plan. What models are going to be used, who's going to do it, what data is going to be collected, what's going to be metered, I just want to mention, I didn't have time to get into it, but there are some little more, I'll call them fancier, sophisticated ways to do calibration error, such as ASHRAE 1423 has some normalized mean bias error, which I've used. And again, when you're in option D, by definition, it means you're relying on simulation models, and there can be disagreements, and that's inevitable across a large number of projects. Just a reminder that EVO, Efficiency Evaluation Organization, you can register online at evoworld.org. evo-world.org, and you can get the core concepts free. Just to put in a plug, upcoming in 2025 will be a new uncertainty assessment guide. You will be able to get that for free. I've confirmed with EVO just by registering and setting up an account on their website. And there's also an option D assessment guide forthcoming later in 2025. So yeah, we can do more question and answer. And just, again, this webinar was sponsored by SEEIT and also Save on Energy and IESO. So there are other tools and resources available there with the Save on Energy. I don't know if Melis, you had any more comments on that, but
Yeah, I just put the actual links in the chat for people
great.
if you're interested to click on them. We do have a post-webinar support intake form, so if you have any questions that we are not able to answer in the next 4 minutes, you can always send them through that form, and we'll be happy to have an expert, probably Eric, answer them through our Save on Energy support. Maybe Eric, there's one question that was asked earlier and that is repeated in the chat about the ASHRAE 14. And I think this was relating the using the CV RMSE to determine the, when we were talking about the 5 versus 10% accuracy. So maybe you want to comment on that. Why would CV RMSE not be a good idea when we're talking about option D?
Well, CVRMSE is it's the standard error divided by the mean from a regression model, and we're not using the simulation models. Like, what's the standard error out of a simulation model? So that's where, I mean, there may be ways to do that, and I'm hopeful there's some better guidance in the upcoming uncertainty assessment guide. But one approach that is used in simulation models is to use like Monte Carlo simulations or repeated number of simulations across a range of input variable parameters. And then you can, by modeling and running hundreds to maybe thousands of simulations, if that's possible, you can come up with essentially a standard error of your modeled result. And then you could use that standard error, divide by the mean of your actual measurements for your as-built system, and you could use a CV RMSE. So that's my best answer to that. The breakdown is you routinely get it out of regression models, and option D usually does not use regression models. So what is the standard error from a simulation model? And again, Monte Carlo, and there's some other fancier mathematical tools that I'm not an expert on. A good question.
That's good.
We do
There
have
was another question earlier. It was not so much a question as a comment, but I wanted to run it by you. So we had this evaluation can't be done until after the decision has been made and the money spent. Would you say that's true?
Dan, yeah. Well, Dan, thanks for joining. I would say often it's done that way, but people who promote real-time evaluation, or it doesn't have to be that way. The best practice of evaluation is to have evaluation involved earlier in the projects and not just swoop in after the fact, if I understand the question correctly. So I would say, if you're talking about like impact evaluation, that like the utility like that IESO would do, if that's what you mean by evaluation, then I would say it's often done that way, but it doesn't have to be. Yeah. Let's see, Mayank, welcome to. I see you had a question in the chat. How would one verify the accuracy of the adjusted baseline? Well, I think I covered that. It's through.
Yes,
you can't calibrate the model to the inefficient system that was never built, but you can build that capability and confidence in the modeling by having, again, the 3 key areas of expertise: M&V, modeling, and process expertise, and doing the calibrated model on the system that was built. And then you just have to extrapolate to the baseline. One other comment, though, you may find this inefficient baseline equipment or system somewhere else, and you could still do some work there if it's worthwhile and it exists and is possible. That could help verify the accuracy of your adjusted baseline.
Thanks, Eric.
Yeah, great questions. So this was more engaging than I thought. I thought it might be very esoteric, unique, and there might be a lot of crickets, but a lot of great questions and a lot of great points made by you folks. So thank you very much. We should let folks go. I can stay on for another few minutes if people want to stay on, but welcome all of you to sign off. And I think I provided my email, mcs@telus.net, which feel free to reach out to me directly if whatever. Thank you.
Thanks, Eric. Thanks everyone for attending.
Bijan, great. A lot of people. Asan, awesome. I didn't see